Every moment, with every breath and every touch, we are in constant interaction with atoms. But her true nature remains a mystery. Join us on a journey to unravel the mysteries of the atomic world, where we will seek answers to fundamental truths about everything we see, touch, and experience. An atom is the smallest unit of ordinary matter that forms chemical elements. Every solid substance, every liquid, every gas and plasma consists of neutral or ionized atoms. At the heart of every atom is the nucleus, which is densely packed with two main types of particles, protons and neutrons. Protons carry a positive electrical charge, while neutrons are neutral and have no charge. Around the nucleus are electrons, tiny particles compared to protons or neutrons, which orbit the nucleus at different energy levels, known as electron shells. These electrons carry a negative charge and are crucial for the bonding between atoms that occurs when atoms share or exchange electrons to fill these shells and achieve stability. Interestingly, despite the central role of these particles, most of the structure of an atom is actually empty space. If you imagine the nucleus as a peanut in the middle of a stadium, the electrons would be like tiny flies buzzing around the stands with large gaps between them and the nucleus. This structure of the atom defines not only the identity of the chemical element, by the number of protons in the nucleus, known as the atomic number, but also its properties and the way it interacts with other atoms. Based on our understanding of the atom, modern science provides a more nuanced definition that goes beyond the simple model of protons, neutrons, and electrons. Today, atoms are recognized not only as the smallest units that retain the properties of an element, but also as units that can combine in countless ways to form anything. From the air we breathe to the materials used in cutting-edge technology. The modern view of the atom emphasizes the quantum mechanical nature of these particles. Electrons, for example, do not move in fixed orbits around the nucleus, as previously thought, but exist in cloud-like regions called orbitals, where the position of each electron is described in probabilities rather than fixed orbits. This quantum mechanical perspective allows scientists to predict the behavior of atoms in complex chemical reactions and even in the advanced materials used in electronics and medicine. In addition, the number of protons in the nucleus, the atomic number, further determines the type of element an atom represents, but isotopes, atoms with the same number of protons but different neutron numbers, show that the atomic mass can vary within an element, resulting in slightly different physical properties. This refined understanding also explains why some elements are radioactive and others stable, affecting everything from geological dating methods to nuclear power generation. The historical origins of the concept of the atom go back to antiquity, in particular to the philosophers of Greece. Around the 5th century BC, a philosopher named Democritus proposed that everything in the universe was made up of tiny, indestructible units, which he called atomos, meaning indivisible in Greek. This idea was revolutionary because it suggested that the changes we see in matter are not due to changes in the basic substances themselves, but in the way these substances are arranged and combined. Democritus theorized that these atoms exist in different shapes and sizes, and that their interactions determine the properties of the materials they compose. Although Democritus's ideas were largely based on reasoning rather than empirical evidence, they laid the foundation for future scientific investigation. For centuries, the concept of atoms was more philosophical than scientific, as there were no experimental methods to test the theory. It was not until the early 19th century that John Dalton, an English chemical chemist, took up the concept and refined it on the basis of his experiments with chemical reactions. Dalton proposed that each chemical element consists of a unique type of atom, and that chemical reactions involve the rearrangement of these atoms. Dalton's atomic theory marked a turning point that transformed the atom from a philosophical to a scientific concept. His work provided the first significant insights into the behavior of matter at its most fundamental level and paved the way for the development of modern chemistry and physics. In the decades that followed, research would not only confirm the existence of atoms, but also reveal the complex internal structures involving protons, neutrons, and electrons, expanding our understanding far beyond Dalton's initial theories and leading us into the realm of quantum mechanics, which defines much of modern science. This journey from ancient speculation to contemporary science shows how sustained curiosity and rigorous investigation can dramatically expand our understanding of the natural world. The Big Bang. The Big Bang Theory is a central scientific explanation for the origin of the universe. This theory states that the universe emerged from an extremely hot and dense state around 13.8 billion years ago and has been expanding ever since. It was first proposed on the basis of observations that distant galaxies are moving away from us in all directions, suggesting that the fabric of the universe itself is expanding. The Big Bang Theory is supported by several important pieces of evidence. The redshift of galaxies, which increases with distance, indicating that the universe continues to expand. The cosmic background radiation, which is the afterglow of the original explosion, now cooled and spread thinly across the universe, can be observed as a faint microwave signal in the sky. And the relative proportions of elements such as hydrogen and helium, which correspond to the predictions derived from the theory. Understanding the Big Bang Theory helps us to ask questions about what preceded that moment and what the ultimate fate of the universe might be. It connects the previously discussed atomic elements, as the intense heat of the early universe was responsible for the formation of the simplest atoms such as hydrogen and helium during a period called nucleosynthesis. These atoms later clumped together under gravity to form stars and galaxies, which initiated the cosmic evolution that led to the complexity of the cosmos today. According to the Big Bang Theory, the universe began around 13.8 billion years ago from an incredibly small, hot, and dense point often referred to as a singularity. This event marks the beginning of space and time, determined by a series of physical conditions that current physics cannot yet fully describe. From this singularity, the universe began to expand rapidly in a process known as cosmic inflation, growing enormously in a fraction of a second. This initial expansion filled the universe with the extremely hot, dense plasma needed to form the basic building blocks of matter. The Big Bang theory not only explains the distribution of galaxies and the cosmic background radiation, but also provides a timeline for the subsequent formation of atoms, stars, and ultimately galaxies. Immediately after the Big Bang, the universe was in an extraordinarily hot and dense state that we cannot directly observe today. During these first moments, the temperatures were so high that particles and antiparticles were created and annihilated in equal pairs. This period is often referred to as the quark epoch and took place within the first microsecond after the Big Bang. During this epoch, the fundamental constituents of matter, quarks and gluons, were in a state of extreme energy and were free of the particles we recognize today. As the universe rapidly expanded, it began to cool, leading to the Hadron epoch about a microsecond after the Big Bang. During this phase, the universe cooled sufficiently so that quarks began to combine to form hadrons, including protons and neutrons, the building blocks of atomic nuclei. About 1 second after the Big Bang, the universe had expanded and cooled down sufficiently to enter the lepton epoch. During this time, leptons dominated matter like electrons, and the universe was densely filled with an extremely hot soup of electrons, neutrinos, and photons. However, it took about 10 seconds after the Big Bang for the neutrinos to decouple and travel freely through space without interacting significantly with other particles. The period of nucleosynthesis began about 3 minutes after the Big Bang. The universe had cooled down to such an extent that atomic nuclei could be formed by the fusion of protons and neutrons. In the first few minutes, most of the helium atoms in the universe were produced, along with other light elements such as deuterium, heavy hydrogen, and traces of lithium and beryllium. This process was largely completed within about 20 minutes of the Big Bang, after which the universe continued to cool and expand, gradually transitioning to conditions that allowed the formation of atoms, stars, and eventually galaxies. This evolution from an almost unimaginably hot and dense point to a state where matter as we understand it could begin to form illustrates the dynamic and violent early history of the universe and laid the foundation for all the complex structures we observe in the cosmos today. Quarks play a fundamental role in the formation of matter, especially in the composition of atomic nuclei, which make up all visible matter in the universe. As the fundamental building blocks of matter, quarks are elementary particles that combine to form hadrons, which include both protons and neutrons, essential components of atomic nuclei. In the early stages of the universe, during the quark epoch immediately after the Big Bang, quarks existed in a free state in a so-called quark-gluon plasma. This was a state of matter in which the intense heat and density prevented the quarks from binding together. As the universe expanded and cooled, it reached a phase in which quarks could no longer exist freely. They began to combine due to the strong nuclear force mediated by gluons. Quark comes in 6 flavors: up, down, charm, strange, top, and bottom. For the formation of matter as we know it, especially the everyday matter that makes up the world around us, the up and down quarks are the most important. These 2 types of quarks combine in different configurations to form protons and neutrons. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The protons and neutrons then group together to form atomic nuclei, the heart of an atom. The number of protons in the nucleus determines the element, such as hydrogen, helium, carbon, and so on, while the number of neutrons can vary within atoms of the same element, resulting in different isotopes. The stability and nature of the nuclei formed depend crucially on the arrangements and interactions of these quarks within the protons and neutrons. In addition, quarks in protons and neutrons are held together by the strong force, one of the four fundamental forces in physics. This force is incredibly strong, much stronger than the electromagnetic force that binds electrons to the nucleus, but acts over a much shorter range. Understanding how quarks combine and interact not only helps to explain the variety of elements in the periodic table and their isotopes, but also the processes such as nuclear fusion and fission that power stars and can be used in nuclear reactors. How did the first protons and neutrons combine? Following the conditions necessary for the formation of subatomic particles in the early universe, the process of nuclear fusion emerges as a key concept for understanding how these particles combine to form more complex elements. Nuclear fusion is a reaction in which two or more atomic nuclei come close enough together to form one or more different atomic nuclei and subatomic particles. This process releases a large amount of energy and is responsible for the energy production of stars, including our Sun. The high temperatures and pressures at the center of stars are ideal for fusion reactions. For example, in the core of the Sun, hydrogen nuclei fuse to form helium at temperatures of around 15 million degrees Celsius. This high temperature provides the necessary kinetic energy that allows protons to overcome their natural repulsion for each other due to positive charges and collide with enough force to combine into a heavier nucleus. While these lighter cores fuse into heavier cores, mass is not perfectly conserved. Part of the mass of the merging nuclei is converted into energy, as in Einstein's equation E equals mc2. This energy output is crucial, not only to maintain the radiation and heat of stars, but also for the synthesis of elements heavier than hydrogen, which happens in larger stars or during supernova events, massive explosions that mark the end of a star's life cycle. Fusion processes in stars are responsible for the formation of most of the elements we find in the universe today, from helium to iron. Protons and neutrons together, known as nucleons, began to fuse under the action of the strong nuclear force, which is the most powerful force over short distances and acts between all nucleons. At that time, the universe was still too hot to bind electrons in orbits around the nuclei, which meant that the particles formed bare nuclei. The first and most fundamental reaction involved the fusion of a neutron and a proton to form a nucleus of heavy hydrogen or deuterium. This reaction is crucial because deuterium serves as an intermediate step in the formation of more complex nuclei. Once deuterium nuclei were available, they could interact with more protons and neutrons to form helium-3 and helium-4. Helium-4 is particularly stable, which made it a common product of these early nuclear reactions. These fusion processes released more energy and enabled further fusion, leading to a slight abundance of helium-4 in the universe, along with traces of other light elements such as lithium and beryllium. The specific conditions of temperature and density required for these reactions meant that they occurred predominantly during a period called Big Bang nucleosynthesis, which lasted for about the first 20 minutes of the universe. Building on the nuclear processes that allowed protons and neutrons to combine to form heavier nuclei such as helium, the formation of even lighter elements such as lithium involved additional specific nuclear reactions that occurred during the early stages of the universe. These processes were part of what is known as Big Bang nucleosynthesis, a series of nuclear reactions that took place within the first 20 minutes of the universe's existence, when it had cooled sufficiently to form nuclei and survive, but was still hot enough to allow nuclear reactions to take place. After the formation of stable helium nuclei, the process of building up lithium began. Lithium, along with beryllium and boron, is considered a light element, and its formation in the early universe was much less efficient compared to hydrogen and helium. The formation of lithium-7, the more stable isotope of lithium, can mainly be attributed to two key processes involving helium nuclei. The most important reaction pathway for the production of lithium involved the fusion of two helium-4 nuclei, alpha particles, to form beryllium-8. Beryllium-8 is very unstable and normally decays back into two helium nuclei. However, in the dense, hot conditions of the early universe, some beryllium-8 nuclei captured another helium-4 nucleus before decaying, leading to the formation of carbon-12. However, the process sometimes took a different route, with beryllium-8 capturing a neutron and turning into beryllium-9, which could then undergo further reactions to eventually form lithium-7. Another route to lithium production involved direct neutron capture by helium-4, producing helium-5, which is unstable and rapidly decays into a proton and a tritium nucleus, hydrogen-3. Tritium was then able to capture another neutron to form helium-4 again, or react with deuterium, hydrogen-2, to form helium-4 and 1 neutron, with further possible combinations gradually leading to the formation of lithium-7. These processes for the production of lithium and other light elements were not as productive as the production of helium due to the specific conditions required and the relative instability of intermediates such as beryllium-8. As the universe continued to expand and cool, the window for these nuclear reactions closed, freezing the abundances of light elements and setting the stage for the chemical evolution of the cosmos. The recombination epoch. The recombination epoch marks a crucial phase in the early universe, typically dated around 380,000 years after the Big Bang, when the temperature of the universe cooled to around 3,000 Kelvin. This cooling allowed electrons and protons, which previously existed in a free state due to the high temperatures, to combine and form neutral hydrogen atoms. This process is called recombination, although it is a little misleading as it was the first time that protons and electrons combined to form hydrogen atoms rather than a recombination of previously combined particles. Before the recombination epoch, the universe was opaque to most forms of electromagnetic radiation because the free electrons scattered photons efficiently. This period is often referred to as the photon epoch. The high-energy photons, particles of light, continuously interacted with the free electrons in a process called Thomson scattering, which prevented the universe from being transparent to light. As the universe expanded and cooled, it reached a state where the energy of photons was no longer sufficient to keep hydrogen ionized, where electrons are separated from protons. The density of the universe also decreased, reducing the frequency of photon-electron interactions and allowing photons to travel longer distances without scattering. This change significantly reduced the probability of an electron absorbing a photon and favored the formation of neutral atoms. Once neutral hydrogen was created, photons could travel freely without being scattered much, which led to the universe becoming transparent to light. This transparency allowed photons to escape what we observe today as the cosmic background radiation, a nearly uniform radiation that fills the universe and provides us with valuable information about conditions in the early universe. In continuation of the recombination epoch, the cooling and expansion of the universe are closely linked processes that are governed by the laws of physics over cosmic periods of time. As the universe expanded from its initial hot, dense state after the Big Bang, it also began to cool down. This expansion can be compared to the effect seen when a gas is allowed to expand. It cools down as it does so. The mechanics of this expansion are anchored in the metric expansion of space, suggesting that it is the fabric of space itself that is expanding. This expansion increases the distance between objects that are not bound by gravity or other forces. As space expands, the energy density of cosmic material, including radiation and matter, decreases. In particular, the wavelength of the witch leads to a decrease in its energy. This phenomenon is known as redshift. For example, cosmic background radiation, which was once the thermal radiation of a much younger universe, is now observed as microwaves due to this redshift caused by the expansion of the universe. The rate of expansion was not constant. It is assumed that the universe went through a short phase of very rapid expansion immediately after the Big Bang, known as inflation. During inflation, the universe expanded exponentially within a fraction of a second, smoothing out irregularities and homogenizing the universe. After this period, the expansion slowed down, which was mainly controlled by the mutual gravitational attraction of all matter in the universe. About 5 billion years ago, however, observations showed that the expansion of the universe began to accelerate again. This acceleration is attributed to a mysterious component known as dark energy, which accounts for about 70% of the total energy density of the universe today. Dark energy, with its negative pressure, is theorized to be responsible for this accelerated expansion as it counteracts the gravitational effects of matter. The cooling of the universe is a direct consequence of this expansion. As the universe expands, the temperature of the radiation that fills the universe decreases. This cooling initially enabled the formation of simple atomic nuclei and atoms, and eventually, as the universe cooled further, the formation of molecules, stars, and galaxies. The following processes of cooling and expansion in the universe. Cosmic background radiation emerges as a critical observational tool for cosmologists. This radiation is the heat left over from the Big Bang, which is now cooled down to very weak microwave light and is distributed throughout the universe. Discovered by chance in 1964 by Arno Penzias and Robert Wilson, the CMB provides a picture of the universe when it was only 380,000 years old, at which time it had cooled sufficiently for electrons to combine with protons to form neutral hydrogen atoms, marking the end of the recombination epoch. B is one of the most important pieces of evidence supporting the Big Bang theory. It tells us that the universe was once in a hot, dense state, as the uniformity of the KMB across large parts of the sky indicates a common origin for all points in the universe. This radiation is not perfectly uniform. Slight variations, anisotropies, in their temperature provide significant insights into the conditions of the early universe, including the density fluctuations that ultimately led to the formation of galaxies and other large-scale cosmic structures. In terms of atom formation, the KMB is directly linked to the time when free electrons and protons first combined to form neutral atoms. The process of electron capture reduced the opacity of the universe, allowing photons to travel freely instead of being constantly scattered by free electrons. The role of gravity. Gravity played a subtle but extremely important role in the formation of atoms, especially as the universe evolved from the simplicity of the Big Bang to the complex structures we observe today. After the cosmic background radiation was released, the universe was mainly filled with an almost uniform gas of hydrogen and helium atoms. The slight variations in temperature and density of this early gas, indicated by the anisotropies in the CMB, were crucial for the role of gravity. These slight variations meant that some regions of the universe were denser than others. Gravity began to amplify these irregularities, as it attracted matter more strongly where it was already somewhat denser. Over time, gravity pulled these atoms together to form gas clouds and eventually stars and galaxies. In these increasingly dense environments, gravity facilitated the accumulation of gas and dust and created the necessary conditions for the nuclear fusion processes that power stars and led to the formation of heavier elements beyond hydrogen and helium. In a broader sense, without gravity, the primordial atoms that were created during the nucleosynthesis phase shortly after the Big Bang would have remained evenly distributed in the universe. There would have been no mechanism to pull these atoms together and form stars and galaxies. Therefore, gravity was not only crucial in structuring the universe on a macroscopic scale, but also in influencing the environments in which atoms could further interact and combine, ultimately leading to the chemical complexity and structural diversity of the cosmos. Stellar nucleosynthesis. After the initial formation of hydrogen and helium in the early universe, the formation of heavier elements mainly takes place within stars through nuclear fusion reactions. This process is called stellar nucleosynthesis, a phenomenon that takes place in the cores of stars as they evolve. In the core of a star, hydrogen nuclei fuse to form helium in a series of nuclear reactions that release a considerable amount of energy. This is the process that powers the Sun and other main sequence stars. When stars have exhausted their supply of hydrogen, they undergo changes that enable the fusion of heavier elements. For stars much larger than the Sun, the increased pressure and temperature due to gravitational collapse allow helium nuclei, alpha particles, to merge. This process forms heavier elements such as carbon and oxygen in a reaction known as the triple alpha process. The triple alpha process requires temperatures of around 100 million degrees Kelvin, which are typical for the cores of red giant stars. The formation of elements heavier than oxygen involves further fusion reactions that can occur in even more massive stars. As the temperature and pressure in the core of the star continue to rise, carbon can be fused into neon, sodium, and magnesium. This progress continues with the fusion of neon and oxygen and so on, creating elements up to iron under increasingly high temperatures and pressures. However, elements heavier than iron require a net energy input to form, which means that they cannot be created by the fusion processes in normal stellar cores. Instead, these heavier elements are synthesized either through the process of neutron capture during the later stages of a star's life and in supernova explosions, the violent deaths of massive stars. In supernovae, the intense energy and neutron flux enable rapid neutron capture by iron nuclei, leading to the formation of heavier elements up to uranium in a process known as R-process fast neutron capture. These heavier elements are then dispersed into space when the star explodes. The ejected material forms the basis for new stars, planets, and ultimately living organisms. This cosmic recycling and enrichment process enriches the interstellar medium with heavier elements that are crucial for the formation of planetary systems and life as we know it. How do stars contribute to the formation of new atoms? During the stable phase in the life of a star, when it is in the main sequence phase, hydrogen atoms in its core fuse to form helium. This fusion process releases an enormous amount of energy that provides the light and heat we receive from stars like our Sun. However, the contributions of stars to the formation of new atoms extend beyond this hydrogen-burning phase. When stars have exhausted their supply of hydrogen, they begin to fuse helium into heavier elements. In more massive stars, this process continues one after the other and leads to the formation of carbon, oxygen, and other elements up to iron through fusion under ever higher pressures and temperatures. This sequence of fusion reactions contributes to the formation of a multitude of atoms that make up the periodic table and defines the life cycle of a star. If a massive star has produced iron in its core, further fusion becomes energetically unfavorable because iron has the highest binding energy per nucleon. At this point, the star can no longer generate the energy needed to counteract its own gravitational collapse. The resulting implosion leads to a supernova, a catastrophic explosion that is crucial for the formation of new atoms. During a supernova, the intense environment and excess neutrons enable the rapid capture process that allows the formation of elements heavier than iron. These include precious metals such as gold and uranium, which are produced in these explosive environments. The materials synthesized from the life and explosive death of a star are then ejected into space, enriching the interstellar medium with new atoms. These atoms are integrated into new star systems, including planets and other celestial bodies. In this way, stars are not only the creators of new atoms through their nuclear processes, but also distributors of these atoms across the galaxy. Telescope. Telescopes are invaluable tools in the study of atom formation, as they provide insights that are fundamental to our understanding of the chemical composition of the universe and the physical processes that occur within it. By observing the light from stars, galaxies, and other celestial bodies, Telescopes help astronomers to decipher the elements present in these objects and the reactions that these elements undergo. The key to understanding atom formation through telescopes lies in the science of spectroscopy. When light from a celestial body passes through a telescope, it can be broken down into its components, creating a spectrum, similar to the way light is split into a rainbow by a prism. This spectrum contains lines known as absorption and emission lines, which are unique for each element and act like fingerprints for atoms and molecules. Each element absorbs and emits light at certain wavelengths. And these characteristic lines in a spectrum allow scientists to identify the elements present in a distant star or galaxy. By studying the spectra of stars, astronomers can, for example, determine the abundance of hydrogen, helium, and other heavier elements and obtain clues as to how these stars were formed and evolved over time. The observation of certain isotopes in stellar spectra can provide insights into the nuclear reactions that take place within stars, including those responsible for the synthesis of new elements. This nucleosynthesis, the process by which heavier elements within stars are created from lighter atoms, is a fundamental aspect of stellar evolution. It is also a crucial component in the life cycle of galaxies, as these elements are eventually dispersed into space when stars die and seed future generations of stars and planets. Telescopes equipped with spectroscopic instruments extend these observations beyond our Milky Way to distant galaxies and provide a broader context for understanding the chemical evolution of the universe. By analyzing the light from the earliest galaxies and comparing it to the light from nearby galaxies, astronomers can trace the evolution of the formation of atoms and the enrichment of the interstellar medium over billions of years. Some of the most significant discoveries about atoms in space have been made through the use of advanced telescopes and spectroscopy, which provide insights into the composition and behavior of matter beyond Earth. These discoveries not only deepen our understanding of the universe, but also clarify the fundamental role of atoms in the cosmos. First, hydrogen and helium abundance. The most abundant elements in the universe, hydrogen and helium, were mainly formed in the minutes after the Big Bang. Observations of the cosmic background radiation and studies of distant quasars and galaxies have shown that these two elements make up most of the ordinary matter in the universe. This frequency provides essential evidence to support the Big Bang model of cosmology. Secondly, heavy elements in stars. Using stellar spectroscopy, astronomers have been able to determine the presence of heavier elements such as carbon, nitrogen, oxygen, and iron in the atmospheres of stars. These observations have confirmed that heavier elements are synthesized by nuclear fusion processes in the cores of stars, a theory that is central to our understanding of stellar evolution and nucleosynthesis. Thirdly, molecules in interstellar space. Beyond individual atoms, spectroscopy has also revealed the existence of complex molecules in the interstellar medium. Molecules such as water, ammonia, and even organic compounds such as methanol were detected. These discoveries are crucial because they suggest the pathways by which chemical complexity arises in space, contributing to the formation of planetary systems and possibly enabling life. Fourth, Isotopic anomalies. Telescope studies have also revealed isotopic variations in the elements found in space compared to those found on Earth. These variations are important for understanding the processes that took place in the early solar system and are crucial for models of how the solar system formed and evolved. Fifthly, helium-3 and deuterium. These lighter isotopes have been observed in the atmospheres of Jupiter and Saturn, as well as in the interstellar medium. Their distribution helps astronomers to understand more about the Big Bang and the processes in the early universe, as their relative abundances are sensitive indicators of the conditions in the first minutes after the Big Bang. Particle accelerators. Particle accelerators are powerful tools that help physicists to study the fundamental particles and forces of the universe. By simulating conditions similar to those immediately after the Big Bang, these accelerators provide invaluable insights into the early universe and the building blocks of matter. At the heart of how particle accelerators work is the principle of accelerating subatomic particles such as protons, electrons, and ions to extremely high energies, and then colliding them at speeds close to the speed of light. These collisions create conditions that are otherwise only found in the universe under extreme environments, such as in the first moments after the Big Bang. When these highly energetic particles collide, they generate temperatures millions of times hotter than the center of the Sun, briefly replicating the hot, dense conditions of the early universe. This environment leads to the formation of a plasma of quarks and gluons, similar to the one thought to have existed during the quark epoch in the first microseconds after the Big Bang. This state is known as a quark-gluon plasma and is of great importance because it allows researchers to study how quarks and gluons interacted before they combined to form protons and neutrons. The energy densities and temperatures reached in these collisions cause the quarks and gluons to be deconfined, which means that they are not bound within particles such as protons and neutrons, but can move freely. This state provides a unique window into understanding the strong force, the fundamental force that holds nuclei together in atoms. Experiments at facilities such as the Large Hadron Collider, LHC at CERN, or the Relativistic Heavy Ion Collider, RHIC in the USA, use these methods not only to study the behavior of matter at these high energies, but also to investigate other fundamental questions in physics, such as the asymmetry between matter and antimatter, the properties of fundamental forces, and the nature of dark matter. By analyzing the particles and forces generated in these high-energy collisions, scientists can test predictions of theoretical physics and explore conditions that cannot be replicated in any other way. Theoretical physicists play an essential role in our understanding of the origins of atoms by developing models and frameworks that explain how atoms and their constituents behave under different conditions. This work is fundamental to bridging the gap between observed phenomena and the underlying principles that govern them, particularly in areas that are beyond the reach of current experimental techniques. Her work focuses on the development of theories that describe the fundamental forces and particles of nature. For example, theoretical physicists have developed quantum mechanics and quantum field theory, which are crucial for explaining the behavior of particles at the atomic and subatomic level. These theories help us to understand why atoms have certain properties and how they interact with each other and with light. Theoretical physicists are also concerned with the implications of these theories and often predict new phenomena that have not yet been observed. For example, the prediction of antimatter was purely theoretical before it was confirmed experimentally. Her work on the fundamental forces of nature, such as the strong and weak nuclear force, has also provided explanations of how nuclei are held together and why certain types of radioactive decay occur. In the context of the early universe, theoretical physicists used their understanding of high-energy particle physics to predict how the universe behaved in the moments after the Big Bang, leading to the formation of the first atoms. Their models of cosmic inflation, for example, describe how the universe expanded exponentially in a fraction of a second during its earliest moments, creating the conditions under which matter as we know it could form. Theoretical physicists also work closely with experimental physicists and provide theories that can be tested and refined on the basis of experimental data. For example, theories about high-energy particle collisions are tested with particle accelerators, as already discussed. Feedback from these experiments helps to refine theoretical models and ensure that they are accurate and applicable to real-world conditions. Our understanding of atoms has changed profoundly over the last century, evolving from a simple model of a miniature solar system to a complex quantum mechanical framework that underpins modern chemistry and physics. At the beginning of the 20th century, the predominant model of the atom, proposed by J.J. Thomson in 1904, was the plum pudding model, in which electrons were embedded in a positively charged sphere. This model was disproved by Ernest Rutherford's gold foil experiment in 1911, which showed that atoms consist of a tiny dense nucleus surrounded by electrons and fundamentally changed the way we visualize atoms. Subsequently, in 1913, Niels Bohr presented his model, which incorporated quantum theory to explain why electrons orbit the nucleus without losing energy and spiraling inwards. Bohr's model introduced the concept of quantized electron shells, in which electrons could only occupy certain permitted orbits with fixed energy levels. This was a significant advance and agreed with the experimental observations of the atomic spectra. The mid-20th century brought further refinements with the development of quantum mechanics, which provided a comprehensive framework for understanding the behavior of electrons in atoms. The Schrödinger equation, formulated in 1920, made it possible to calculate electron probabilities instead of precise locations, and introduced the concept of electron clouds and orbitals instead of fixed orbits. This model better explained chemical bonding and the properties of atoms that interact to form molecules. In recent decades, our understanding has expanded beyond the electron cloud model to look at the substructure of the atomic nucleus itself, which consists of protons and neutrons and is dominated by the strong nuclear force. We have discovered that protons and neutrons are not fundamental particles, but consist of quarks bound by gluons, as described in the theory of quantum chromodynamics. Experimental and theoretical advances have led to the standard model of particle physics, which not only explains the behavior of known particles, but also predicts the existence of other particles such as the Higgs boson, which was discovered in 2012. This model continues to be tested and extended as we study conditions that replicate the early universe in particle accelerators and further refine our understanding of atomic and subatomic processes. What is quantum mechanics? Quantum mechanics fundamentally changes our understanding of atomic behavior by providing a mathematical framework that describes the properties and interactions of atoms at the smallest scales. In contrast to classical physics, which predicts exact results based on given inputs, quantum mechanics deals with probabilities and uncertainties. One of the core principles of quantum mechanics is wave-particle duality, which states that every particle or quantum entity can be described as both a particle and a wave. This concept is crucial for explaining the behavior of electrons in atoms. Instead of orbiting the nucleus in neat, planet-like orbits, as previous models suggested, electrons are described by wave functions that predict a statistical distribution of the positions they can occupy around the nucleus. These are the so-called electron orbitals. The Schrödinger equation, a key element of quantum mechanics, enables physicists to calculate the wave functions of electrons for a given atomic system. These wave functions do not indicate the exact location of an electron at a specific point in time, but describe a cloud of probabilities as to where the electron is most likely to be found. This approach explains why certain atomic behaviors, such as electron configurations in chemical bonds and the absorption and emission of light, occur in specific quantized, discrete ways. Quantum mechanics also introduces the concept of quantum superposition, where particles exist simultaneously in all possible states until an observation is made. This principle is illustrated in the famous Schrödinger's cat thought experiment, in which a system can be in several states at the same time until it is observed. Another fundamental principle of quantum mechanics is Heisenberg's uncertainty principle, which states that it is impossible to know both the exact position and the exact momentum of a particle at the same time. This principle is crucial to understanding atomic behavior because it implies that at the subatomic level, there is a fundamental limit to what can be known about the location and velocity of a particle. This has profound implications for predicting the behavior of electrons in atoms and molecules. Through these concepts, quantum mechanics provides a comprehensive description of how atoms interact, form molecules, and participate in chemical reactions, which classical physics could not adequately explain. Quantum fluctuations. Quantum fluctuations are a fundamental concept in quantum mechanics and describe the transient changes in the amount of energy at a point in space, as prescribed by Werner Heisenberg's uncertainty principle. This principle states that it is impossible to know both the position and the momentum of a particle with absolute precision at the same time. One of the remarkable consequences of this principle is that energy and time are also uncertain to a certain extent. This uncertainty enables the creation of particle-antiparticle pairs from the vacuum for very short periods of time. These particles and their corresponding antiparticles emerge briefly and almost immediately annihilate again, returning the energy borrowed from the vacuum. Although these events are incredibly short-lived, they are real and have measurable effects such as the Casimir effect and the lamp shift. For example, the Casimir effect can be observed as a small attractive force between two uncharged parallel plates in a vacuum caused by the reduction in the number of quantum fluctuations between the plates compared to outside. In the context of cosmology, it is assumed that quantum fluctuations during the inflationary period of the early universe are the origin of all structures in the universe. Tiny fluctuations in the density of the universe were amplified during inflation, resulting in the large-scale structures such as galaxies and galaxy clusters that are observed today. Quantum mechanics has significantly advanced our understanding of atom formation and behavior. But there remain several unresolved questions that continue to challenge physicists and influence our understanding of atomic and subatomic processes. Addressing these questions is crucial for the development of a more complete theory of matter and the universe. First, wave function collapse. One of the central mysteries in quantum mechanics is the collapse of the wave function. The wave function describes the state of a particle in probabilities until it is observed. At the moment of observation, it seems to collapse into a specific state. How and why this collapse occurs is not well understood and poses a fundamental question about the nature, reality, and measurement in quantum mechanics. Second, quantum gravity. Understanding gravity in quantitative terms remains elusive. The theories of general relativity and quantum mechanics describe the universe on large scales and at the atomic level, but are currently incompatible when it comes to describing gravitational effects on a quantitative level. This incompatibility becomes significant when considering the early universe, where the quantitative effects of gravity may have influenced the formation of the first particles and atoms. Thirdly, the role of dark matter. It is known that dark matter exerts gravitational forces and thus influences the structure and development of the universe. However, their role on a quantitative level and their interaction with normal matter remain poorly understood. Insights into dark matter could reveal new aspects of atom formation, especially in the early universe. Fourthly, matter-antimatter asymmetry. Quantum mechanics does not fully explain why there is significantly more matter than antimatter in the universe after the Big Bang. This asymmetry affects our understanding of the composition of the early universe and the fundamental forces that determined the formation of atoms. Fifth, quantum entanglement and non-locality. Entanglement, in which particles are linked in such a way that the state of one particle, regardless of distance, immediately affects the state of another, raises significant questions about information transfer and causality. This phenomenon could have implications for understanding the interactions within early cosmic states, where entangled particles may have influenced the atom formation processes. Created out of nothing. The creation and formation of atoms is understood from a scientific perspective through the principles of nuclear physics and cosmology. However, different cultures have their own unique interpretations and mythologies regarding the origin of matter, often embedded in broader creation myths that offer insights into their worldviews. First, Western philosophical traditions. The concept of indivisible basic units of matter comes from the ancient Greeks, in particular from philosophers such as Democritus and Leucippus, who introduced the idea of atomos, which means indivisible. This idea was purely philosophical and speculated that everything in the universe consisted of these indivisible units and the doctrine. Secondly, Hindu cosmology. In Hinduism, The creation of the universe is seen as a cyclical process involving the creation, destruction, and rebirth of the universe. The ancient texts of Hinduism, such as the Vedas and Upanishads, speak of the elements Panjabhuta, earth, water, fire, air, and ether, which are regarded as the fundamental components of the universe. While they do not speak directly about atoms in the modern sense, these elements can be seen as philosophical equivalents to the fundamental building blocks of matter. Thirdly, Buddhism. In Buddhist philosophy, especially in the Abhidharma teachings, there is the concept of dharma, which can be seen as the ultimate components of reality. These are not atoms in the physical sense, but tiny phenomena that come together to form the perceived world. The focus here is more on the transience and interdependence of all entities than on a permanent structure such as atoms. 4 indigenous perspectives. Many indigenous cultures around the world, including the Native Americans and the Aborigines of Australia, have creation stories that focus on the harmonious interplay of natural forces and entities. While they do not explicitly mention atoms, these stories often describe the creation of the universe in terms of elemental forces and the life-giving aspects of earth and sky, emphasizing balance and unity in the cosmos. Fifth, Islamic and Middle Eastern views. In Islamic philosophy, especially during the Golden Age of Islam, scholars such as Al-Hasan and Avicenna considered the nature of matter. Although their understanding was influenced by Greek atomistics, they often integrated these ideas with theological principles and saw the continuous creation and organization of atoms as an expression of divine order. These different cultural views reflect different understandings and interpretations of the fundamental nature of the universe. While modern science provides a universal framework to understand atom formation based on empirical evidence and mathematical laws, these cultural narratives offer a broader, often more philosophical perspective on the origins and nature of matter, and show how different societies have sought to understand the world around them. Ethics in research. The study of the origins of the universe, particularly through disciplines such as cosmology, astrophysics, and particle physics, brings with it significant ethical considerations surrounding the allocation of resources, the environmental impact of large-scale research activities, and the broader philosophical and existential issues. The questions that such investigations can raise. A key ethical issue is the allocation of significant financial and material resources required for high-energy physics experiments such as those at facilities like the Large Hadron Collider, LHC, at CERN. Critics argue that the enormous investments involved could be better used to solve urgent global challenges such as poverty, healthcare, or education. However, supporters of these projects argue that the potential technological and intellectual advances justify this expenditure due to the long-term benefits they are likely to provide. In addition, the environmental impact of operating large scientific equipment, including the significant energy consumption and environmental footprint of building and maintaining such facilities, poses serious ethical dilemmas. Given the high energy requirements of particle accelerators, for example, there are implications for CO2 emissions that need to be carefully considered and possibly mitigated through the use of renewable energy sources. Beyond practical concerns, delving into the origins of the cosmos can lead to profound philosophical and existential reflections that can challenge and potentially transform our understanding of the universe and humanity's place within it. The ethical implications of such knowledge raise questions about the existential risks posed by emerging and the philosophical implications of discoveries that could fundamentally shift human perspectives on life and our responsibilities towards each other. Investigations into the beginnings of the universe could also conflict with cultural and religious beliefs about creation and existence, which could lead to ethical conflicts about how these topics are treated in public discussion and in educational institutions. The balance between respecting different points of view and promoting scientific literacy requires a nuanced and thoughtful debate. There is an ethical responsibility to consider the impact of today's scientific discoveries on future generations. The knowledge and technologies we are developing now can have far-reaching effects that go far beyond the present and influence the future of humanity and other life forms that exist or could emerge. As our understanding of quantum mechanics and cosmology continues to advance, future theories of the origin of atoms could likely extend or radically alter our current model by incorporating new discoveries and technological advances. These future theories could explore deeper connections between quantum field theory, string theory, and unexplored aspects of particle physics, potentially providing a more comprehensive understanding of how atoms and other particles came to be. Future theories? First, unified field theories. One promising area is the development of a unified field theory, often referred to as a theory of everything, which could seamlessly integrate the four fundamental forces of nature: gravity, electromagnetism, strong nuclear force, and weak nuclear force. Such a theory could explain how these forces interacted at the beginning of the universe to create the first particles that led to the formation of atoms. Secondly, quantum gravity and the early universe. Future theories may also offer new insights into the role of quantum gravity, particularly during the formation of the universe known as the Planck epoch. Understanding gravity on quantitative scales could explain how atomic particles behave under extreme conditions. This could also influence our understanding of the space-time fabric and its influence on particle formation. Thirdly, multiverse theory. Another theoretical frontier is the multiverse theory, which postulates the existence of several, possibly infinite universes with different physical laws. Future research could investigate how different physical constants in alternative universes could lead to different types of atomic structures or new forms of matter, which could expand our understanding of particle physics in unexpected ways. Fourth, dark matter. With a clearer understanding of the nature of dark matter, future theories may reveal how this mysterious substance influenced the energy field of the early universe and contributed to atom formation. Understanding the properties of dark matter could lead to breakthroughs in how we understand the mass and energy that influenced the early stages of the universe. Fifth, particle accelerator technology. With advances in particle accelerator technology and observational astronomy, we may be able to simulate and observe conditions closer to the Big Bang more accurately than ever before. These technological innovations could lead to new discoveries about the very first moments of atom formation, testing the limits of our current models and potentially requiring new theoretical frameworks. Mystery of dark matter. Dark energy, a mysterious force that accelerates the expansion of the universe, interacts subtly with atomic matter, although its primary effects are visible on the scale of the entire universe rather than at the level of individual atoms. Dark energy is an elusive concept that has puzzled astronomers and physicists since its discovery in the late 1990s through observations of distant supernovae. These observations showed that the universe was not only expanding, but accelerating its expansion, a phenomenon that could not be explained by existing theories of gravity and cosmology, which predicted that the expansion should slow down due to the gravitational attraction of matter in the universe. It is estimated that dark energy accounts for about 68% of the total energy in the observable universe, but remains poorly understood. In contrast to dark matter, which interacts with atomic matter through gravity and is therefore detectable through its gravitational effects on visible matter in galaxies and galaxy clusters, dark energy does not clump and does not interact with light. Instead, it appears to have a uniform presence throughout space, exerting a repulsive force that influences the rate of expansion of the universe. At the atomic level, the direct interaction between dark energy and matter is negligible. The influence of dark energy is mainly gravitational and macroscopic and affects the fabric of space-time itself. It acts more like a property of space than a force that acts directly on particles such as protons, neutrons, and electrons that form atoms. However, dark energy plays a crucial role in the large-scale structure of the universe, indirectly influencing the formation of galaxies and galaxy clusters in which stars and ultimately atomic matter are formed. The exact nature of dark energy is one of the most fascinating mysteries of modern physics. It is often modeled as a cosmological constant, a term that Albert Einstein originally introduced into his equations of general relativity and later described as his biggest mistake. Alternatively, some theories suggest that it could be a field, similar to the electromagnetic field with its own dynamics and particles. Further research and new technologies such as more advanced space telescopes and observatories are expected to shed light on this profound component of the universe which, although immensely powerful on cosmic scales, escapes direct detection at the atomic level. Dark matter is a form of matter that does not emit, absorb, or reflect light, and is therefore invisible and only detectable through its gravitational effects. It is estimated to make up about 27% of the mass-energy content of the universe, considerably more than the ordinary matter that makes up stars, planets, and living organisms. The exact nature of dark matter remains one of the most intriguing mysteries in physics, as it has not been directly observed and its properties are inferred only from its gravitational influences on visible matter and cosmic structures. Dark matter mainly influences atom formation indirectly through its influence on the gravitational structure of the universe. It plays a decisive role in the formation of galaxies and large-scale structures. After the Big Bang, the universe was an almost uniform field of energy and matter, but slight density fluctuations, quantum fluctuations, became the seeds for structures in the universe. Dark matter began to clump around these density fluctuations due to its gravitational attraction. These clumps strengthened the gravitational fields, attracted ordinary matter, and led to the formation of stars and galaxies. Without dark matter, the gravitational force needed to collapse these regions into galaxies might not have been sufficient, resulting in a very different universe. The presence of dark matter created the gravitational wells that guided ordinary matter to form dense regions in which stars and consequently galaxies could form. Within these galaxies, atomic matter, ordinary matter continued to develop, forming new stars and planetary systems. Although dark matter does not interact with atomic matter through the electromagnetic force, meaning that it does not directly influence atom-forming processes such as nuclear fusion, its gravitational effects were crucial in shaping the environments in which such processes could take place. By influencing the formation and evolution of galaxies, dark matter created the necessary conditions for the formation of stars and the subsequent synthesis of heavier elements in these stars, which are crucial for the diversity of matter observed in the universe. Antimatter. Antimatter played a significant role in the early universe, particularly immediately after the Big Bang, and shaped the basic structure and composition of the cosmos we observe today. Antimatter is similar to matter in that it has mass and volume, but its electrical charges are opposite. For example, an electron, a particle of matter, has a negative charge, while its antimatter counterpart, the positron, has a positive charge. In the first moments after the Big Bang, the universe was extremely hot and dense and filled with a high-energy soup of particles and radiation. Under these conditions, both matter and antimatter were created in abundance by processes in which high-energy photons converted their energy into particle-antiparticle pairs. A phenomenon that was predicted by quantum field theory. These include pairs such as electrons and positrons, protons and antiprotons, as well as neutrons and antineutrons. According to theoretical predictions and observations of cosmic background radiation and other cosmological data, matter and antimatter should have been created in almost equal quantities. However, a small asymmetry in favor of matter made the existence of matter in today's universe possible. This slight imbalance meant that for every billion matter-antimatter pairs, one additional matter particle existed. This excess matter was crucial as the universe cooled and particles began to coalesce. Matter and antimatter annihilated on contact and released energy in the form of photons. If matter and antimatter had been perfectly balanced, this annihilation would have left the universe without matter from which stars, planets, and galaxies could form. The reason for this asymmetry remains one of the great unsolved questions in physics and is the subject of ongoing research. Theories propose mechanisms such as CP violation that could explain differences in the behavior of matter and antimatter. CP violation has been observed in certain subatomic particles under conditions achievable on Earth and provides clues, but not a complete answer, to the matter-antimatter asymmetry in the early universe. Dimensions and atoms. The idea that alternate dimensions influence the behavior of atoms is an intriguing concept in theoretical physics and is largely based on discussions around string theory and other complex theories that aim to unify the fundamental forces of physics. String theory proposes that what we perceive as particles are actually one-dimensional strings vibrating at certain frequencies. These strings could possibly exist in more dimensions than the 4, 3 spatial, and 1 temporal that are part of our daily experience. The extra dimensions postulated by string theory are considered to be compacted or curled up to such small scales that they escape current experimental detection, yet they could be an integral part of the universe. In the context of atomic behavior, if string theory or similar multidimensional theories are true, they could provide explanations for some of the phenomena that the standard model of particle physics cannot fully explain, such as why particles have the masses they do, or why the forces of nature are scaled the way they are. The behavior of atoms and subatomic particles could be subtly influenced by interactions taking place in these extra dimensions, potentially affecting everything from the fundamental properties of the particles to the forces governing their interactions. However, there is currently no direct experimental evidence to confirm that these additional dimensions exist or influence atomic behavior in an observable way. High-energy physics experiments, such as those conducted at the Large Hadron Collider, are actively searching for phenomena that could be interpreted as signs of additional dimensions, such as unexplained energy and momentum losses that could escape into these dimensions during particle collisions. These experiments have not yet provided confirmation of additional dimensions, but continue to push the boundaries of our understanding, particle physics, and the structure of the universe. Exotic particles. Exotic particles, a term generally used to describe particles that do not fit into the traditional particle physics model, called the Standard Model, represents some of the most intriguing and least understood aspects of physics. These particles often exhibit properties or behaviors that challenge existing theories and could potentially reveal new physics beyond our current understanding. One of the best-known types of exotic particles is the tachyon, theoretically predicted but never observed. Tachyons are hypothetical particles that travel faster than light, and if they exist, they would have profound implications for theories of relativity and causality. Another example is magnetic monopoles, particles proposed to have a single magnetic charge, either north or south, as opposed to the normal magnetic dipoles such as the ordinary magnet. Although predicted by certain large-scale unification theories, magnetic monopoles have not been empirically proven. The influence of exotic particles on atom formation could be significant, especially if their existence were proven, as they may interact in unusual ways with the fundamental forces of nature. For example, if magnetic monopoles exist, they could significantly alter the electromagnetic fields, which in turn could affect the way atoms and molecules bind and interact. Such changes could potentially lead to the discovery of new types of chemical reactions that are not possible under the current understanding of physics. The presence of exotic particles such as tachyons could lead to new models of energy transfer and particle interactions at the subatomic level, potentially offering insights into the early moments of the universe where conventional physical laws may not apply. These particles could provide clues to the unification of forces and particles under extreme conditions, similar to those that prevailed shortly after the Big Bang, and influence how atoms and complex molecules first formed. Challenges and limitations. The study of atom formation presents several significant challenges and limitations. mainly due to the complex and often elusive nature of the processes and particles involved. A major limitation is the scale at which these processes take place, both in terms of the incredibly small size of the and the high energy levels that are often necessary to study them. These factors make the direct observation and manipulation of atomic and subatomic particles extremely difficult. The instruments needed to study atom formation, such as particle accelerators and powerful telescopes, are not only enormously expensive to manufacture and maintain, but also require a high level of technical expertise to operate. The Large Hadron Collider, LHC, for example, is one of the most complex and expensive scientific instruments ever built, operating at energy levels that replicate conditions that prevailed a fraction of a second after the Big Bang. The sheer cost and complexity of such equipment can limit the scope and frequency of experiments. Another significant challenge is the theoretical nature of much of the physics involved. Many theories of atom formation, especially those that go beyond the standard model of particle physics, remain largely speculative and are often difficult to test empirically. For example, theories involving dark matter and dark energy are critical components that are thought to influence atom formation in the early universe. Limited by our current inability to recognize these substances directly, researchers rely on indirect observations and the gravitational effects that these entities theoretically have on visible matter, making the study and validation of hypotheses difficult. New theories about atoms have the potential to fundamentally change our understanding of science in various disciplines, from chemistry and physics to biology and cosmology. Atoms, the building blocks of matter, have been studied for centuries, and each advance in our understanding of their structure and behavior has led to significant changes in scientific thinking and technological innovation. If new theories were to emerge that offer deeper insights into atomic structure or introduce new properties of atoms, the implications could be profound. For example, a new understanding of quantum mechanics could lead to more accurate predictions of atomic interactions and potentially revolutionize chemistry. This could lead to the development of new materials with unique properties, such as superconductors that work at room temperature, materials with exceptional hardness or flexibility, or drugs that are precisely designed to interact with the body at the molecular level. In physics, new atomic theories could influence our understanding of fundamental forces and particles, and led to a more unified theory that combines quantum mechanics with general relativity. Such a theory could provide new insights into the behavior of matter under extreme conditions, such as inside black holes or at the time of the Big Bang, and change our understanding of the origins of the universe and its ultimate destiny. Furthermore, advances in our understanding of atomic theory could have practical applications in technology, such as the development of quantum computers. Quantum computing uses the principles of quantum mechanics to process information in a fundamentally different way to conventional computers. A deeper understanding of atomic interactions and quantum states could accelerate the development of quantum computing technologies that could potentially solve problems that are currently unsolvable for classical computers. In the energy sector, Better knowledge of atomic processes could lead to more efficient energy sources. For example, understanding the mechanisms of nuclear fusion, the process that powers the sun, could lead to the development of more sustainable and efficient fusion reactors on Earth, and provide an almost unlimited source of clean energy. Final thoughts. As we complete our journey to discover how atoms were created from nothing, we realize that we are not only learning about the origins of the universe, but also exploring profound mysteries about existence itself. This search for the emergence of everything from an apparent emptiness challenges our view of the world and deepens our understanding of what it means to really exist. Do you believe that atoms and everything we know were created from nothing? Or are there other unknown forces involved? Let us know your thoughts in the comments below. Thank you very much for watching.